I took a lab term work for you, but because of some network issues and all, I was unable to complete it. Okay. So today, first I'll just do a revision of the third term work itself. The term work which we left on Saturday, okay? Because of that problem, the issue, we were unable to complete it. So it's better I'll just complete the term work first again, okay? Shall I start it from the beginning? The term work in the chat box, anybody for me? It will be a revision also for you. Yes, fine. Yeah, that would be better. So just another 2 more minutes and we'll start it, okay? Let people join. Early Monday morning, people are joining. Just it's 10:02 in my watch. By 10:05, I'll start it, okay? Without wasting much of your time also. And see, all your attendance is being recorded, okay? The Google form is just for mandatory. It is not mandatory actually. It is just a formality, but in this session, we can just keep track of how many were online, how many had logged out and all. So please make sure that you are in the classrooms, okay? Just filling the Google form doesn't mean that you are present for the class, because we can get a live session of your recordings also, that who was there in the class for what time and all, okay? So please make sure that you are in the classrooms. Just 1 more minute and we'll start it, okay? Okay. Twenty-seven people are there. Just 2 more minutes and we'll start our presentation. Okay, meanwhile people join, let's start it, okay? Okay. So in the previous class, that is on Saturday, we were discussing the term work, which is nothing but the 6 term work from the syllabus copy. The first was done by sir, first two. Third was done by Prashant sir, file locking. Fourth one was done by me, that is IPC, interprocess communication. And now sixth one, since it deals with the process part, this is one which I am taking for you, the race condition, because this all deals with the process. So again, as I started, let's understand theoretically first what is a race condition here. As we all know now, since the same example, I'll take it, okay, for you again. So assume that there is a classroom going on, or assume that you have a friend circle first. So your friend circle, on a weekend, you are just hanging out somewhere and you people are talking with each other. So sometime one fellow had gone for some outing and all, he comes back and other people keeps on asking him. Chalo, now as a trend, Kitwad Falls is in boom, right? Many people are visiting there. So one of your friend will go and come back. So rest of the people who want to go, they keep on asking the question to that friend, right? Hey, how was the falls? How far it is? Whether you have a car parking there? Whether you have any eatables, things and all. So many people will keep on asking the question for you, right? So see, 5, 6 people are asking the question to you itself. Now, whom will you answer first? Because what is happening here is the 5, 6 people are asking us different questions to you itself, because you are the only person here. Now, whom will you respond? Yeah, one fellow of yours will ask, "How was it?" Okay, so let's take the same example in the classroom only now. Okay, now assume that teacher is taking a class here and students are attending the classes. Okay, so once the class gets over, as I said, teacher will ask any doubts. So none of the students will say that, "Sir, ma'am, or sir, I have a doubt here." But again, after forcing teacher again and again, if anybody has any doubts, then somebody will say that, "Sir, I have a doubt." So once they say I have a doubt, teacher will ask, "Okay, ask me your doubt." So he or she will ask the doubt and teacher will clarify the doubt. Okay, so this doubt is clear now, because there are 6 people in the classroom and only one fellow is asking a question to the teacher. So it is easy for teacher also to respond, because only one fellow is asking, so teacher will respond to that student. So once it is done now, once it is done, then the next task comes is rest all people will start their doubts now. How many people will have the doubts? So since there is a single teacher and many people have the doubts, all of them will keep on asking the doubts to a teacher. Everybody will ask, "Sir, what is this? Sir, what is this?" Now see the scenario. So many people are asking different doubts to a single person. So what is happening here? n number of people are here. They have their own doubts. They have their own doubts, and they ask teacher. Now, whom will the teacher respond first? The next question comes is, who will, because there is a single teacher and many students. So now, whom will the teacher respond? Now, that depends on the teacher itself, right? There are many scenarios, as I told in Saturday's class also. The first scenario may be teacher may follow first come first serve. Whoever was first to ask the doubt, that doubts get clarified. Assume that this is a person who was first who was asking doubts, so that doubts get clarified. Then probably this was a second, so second doubt is clarified. Then he was a third, then third doubt get clarified. One way of addressing the doubts. Second way is, since all these three are asking doubts, now teacher may have a lookout. His question is very lengthy or very difficult to answer, but his is very easy. So teacher may use this policy. He may answer this questions out first. Yeah. Then may go to this, then may go to this. No matter he was the first who was asking the doubt. Right? Right? Again, it may so happen that this was the fellow who had asked last, but his question was very easy. So teacher would address his first. So now the scenario what I want to tell here is, if n number of people are asking doubts to a single person, and now how this person will respond will depend on the person itself and not on the questions how they have arrived. Right? Depends on the person itself. So what happens here is, if n number of people are asking a doubt to a single person, whom to respond depends on the teacher itself. And now you can't predict. Since I was the one who was asking doubt first, so I'll be answered first. No. I was the one who was asking doubt, so I'll get answer. No. So there may be various scenarios on whom they may answer. And the first scenario may be whose question is very easy. See, three people are asking the doubts, and the first person whose question is second person whose question is very easy. So teacher may address that first. There may be again scenario. Maybe he or she is a CR in the class. So it is better to answer the CR's doubt first, right? Yeah. So that may be one of the answers. Or whose answer is known to them. Maybe three people are asking the doubts. Two or teacher is unaware about that or not confident. But the third answer, she is confident. He or she is confident. So they may address that first. And there are various factors. And various factors. And the very important factor which I told is between the switching between the answers. Now, what I mean by switching between the answers, see this scenario. Now, first person asks a doubt. So the question is thrown to the teacher. This question is thrown to a teacher, and teacher addresses this. So meanwhile, rather than answering all his questions, maybe this fellow has three doubts. So he'll answer first doubt, teacher will answer the first doubt. Second doubt, teacher will answer the second doubt. But still he has third doubt. But meanwhile, what the teacher might do is, teacher might stop him, you wait, I'll answer his or her doubt. What is happening here is switching between the answer is happening. Switching between the answers. So the teacher may come here, may answer his doubt, then again may go here, answer his doubt, come back, then may come to this fellow. That is what happens in your classrooms also. When you ask a doubt to a teacher, one person's doubt teacher will ask, and just wait now, I'll switch to other person, we say, and these things happen. So this is because of, we call it as a context switching. So on similar lines, we also have a race condition. Now what is a race condition is, when n number of people, see here, now these are n number of people who are asking a question to teacher. Now if he is the one who's asking first, you cannot predict that his answers will be addressed first. If he is the one who's answering first, you cannot say that he'll be addressed first. If he is the person who has only one question, doesn't mean that he'll be answered first. Now, whom to answer and how to answer depends on the teacher. So on similar lines also, in the system now, there are n number of processes running. And if n number of processes, assume that now this is a process 1, process 2, process 3, process 4, 5 and 6. So if n number of processes are running, and all these processes are trying to do something with the shared data. Now this is the shared data. See, the teacher is shared among all the 6 people. Similarly, the n number of processes share a shared data. Now once they share the shared data, the output depends on how the teacher responds. Okay, and this is called as race condition. That is what I'm talking technically now. Now race condition occurs when multiple processes are trying to do something with the shared data. and the final outcome depends on the order in which the process runs. Now you can't predict which process runs first, because again there is one more important concept here, students, which is called as context switching. As I said, switching between the answers happens with the teacher level. In the system also we have a context switching. Now what is a context switching? It is a concept in which kernel allocates timing for each process. Now there are user processes and there is a kernel processes, usually called as a user mode and kernel mode. Now how the timing is given for each is depend on the kernel. Kernel switches the process from user mode to kernel mode and vice versa. Now how does the kernel does the switching? It depends on the system, depends on the resources available, depends on the scheduling algorithm, and all it is. So we cannot predict in which the process will run first. Even if I know he was the first who had asked the question, but it always doesn't mean that his answers will be solved for me. So context switching is a concept in which kernel decides whom to switch the control of the system, whether to the user or to the kernel. Okay, this is called as context switching. So how this raise condition will occur in the systems? This will occur with the help of a fork function. Now fork is a system call which helps to create a child process. Okay, this was the initial scenario about what is the raise condition. See here, when multiple processes are trying to do something with the shared data, the outcome depends in way the process executes. In the way process executes, and you can't predict which process will execute first. This is because of the context switching concept. So same thing is explained here theoretically. Race condition occurs when multiple processes are trying to do something with the shared data, and the final outcome depends in the order in which the process runs. Now how I can demonstrate a race condition? This can be done with the help of a fork system call. See here, that is what I said here. Even if you know which process runs first, what happens after the process starts depends on the system load and kernel scheduling algorithm. Maybe I am the one who is starting first, but I'm not getting all the resources. Then I'll be in a halt mode. Yes. So that is what happens at the system also. N number of processes are running. N number of processes are running. But still it depends on the kernel which process to give the authority and which not to give. Okay. Now this is what the theoretical. It always runs with the parent and child. So whenever I want to demonstrate a race condition in a system, I should have two processes. So usually I'll have a parent process and a child process. So how it can be done? It can be done with the help of a fork system call. Now fork is a system call which has a data type PID_T, which writes the process ID of a process. Okay. So fork is a system call which creates a new process. Usually I call it as a child process. Okay. And very important thing to remember here is whenever the fork system call is executed, it has two return values. See, this is the only function which has two return values. Which are the two return values? If it creates a child process successfully, it writes 0 to the child, a status 0, saying that you are created successfully. And at the same time, whichever child was created, its process ID. Remember the inode number I told in the second chapter, every file has a unique number. Similarly, every process has an ID. We call it as a process ID, and that process ID is told to the parent process. So this is what happens with the fork. It writes 0 in the child process, and it writes the child ID to the parent, and it writes 1 on error. Okay. Now how does the fork executes here? The minute you call fork in a main function, it creates a child process. So the minute a child process gets created, it writes 0 to the child. 0 is a status saying that the child is created. And after that, it writes the child ID to the parent process. Now how this I can get it? There is a concept known as get PID. Get PID will get the process status of the process ID of the current process, and get PPID, that is get parent process ID, is nothing but the ID of the parent who created the child. Okay, so this I'll just show you here as a demonstration now, which I had left in the previous class. Okay, so there is a concept here. Just I've written a main. I've defined a variable PID of the data PID_T, which is nothing but the stores the process ID. So I'll call a fork. Now what is a fork? It creates a child process. That is only I know now. So once it creates, it writes its process ID in PID. So if you want to know what is the ID of this child process created, you can get it by the system called get PID. Get PID gets me the process ID which is created, and get PPID is the process ID of the process who created this child process. Okay, let's see now. You'll understand here. See, it will take 2 minutes for time. So just a minute, let it run. It's running. Just give me 2 minutes. It's running here. It's running. Why? Because every time when you run, right, you get a new ID every time. So it is better to run this only one time. This is nothing to do with the lab term work. Just I want to tell you the concept of get PID and get PPID. That's it. Running. You'll understand why did not I compile and keep it initially. Okay, I tell you, because every time when you run, it creates. Okay, got the output. See it. See the window here now. Okay, it keeps on displaying n number of times for you. Now child process ID is 8547 and the parent process ID is 8546. See here, this is obviously a number below that is a parent process. So this parent created this child process, which is nothing but the ID of this child process, and every time it keeps on displaying you again and again. Okay, this is at the system level now. Again, for the previous process, this becomes a child and its ancestor becomes a parent process. So with the system called get PID and get PPID, you can get the child process ID and the parent process ID. Okay, now coming back here, as I said, child and process. Now you may say, so why it writes 0 to the child and it's write its ID to the parent? This will clear your doubt. See, logically speaking, a parent can have n number of child process, n number of child process. But for all this child process, there will be always a single parent. So it is easy for parent to remember the child ID, right? But difficult for parent to remember the child ID. It is easy for child to remember its parent ID. Take an example of your class itself now. The very first day when you go to a class, maybe you came very first day for the 4th semester in the class. I give the same example here. See, those examples are being related here. It is easy for 60 people to remember a staff name. Yeah, it is easy for 60 people to remember a staff name, but difficult for a staff to remember all the 60 names. So only I keep on getting the attendance sheet for you, right? So in attendance sheet, all your USNs are there. So your USNs is told to teacher, and you say present or absent, and it is very easy for you to remember the teacher name, right? This is what happens in system also now. A parent process can have n number of child process. So it is difficult for parent to remember all the child process. So those child process IDs are given to the parent. So parent, it writes the child ID to the parent. Now parent keeps track of, I am having 1, 2, 3, 4 child. It can keep track of all those 4 child by their ID. So once process terminates, the ID is gone. And it writes 0 to the child saying that you are created. Now child knows, I am a child created from this parent. So only fork has 2 return values. It writes 0 to the child saying that you are created successfully, and this process ID is given to the parent process. Okay, now this is clear. Now that is what I told, the simple example how you can get it. Now let's understand how I can implement a race condition. Okay. Now this is what is told here. See, the reason child process ID is returned to the parent is that a process can have more than one child, and there is no function that allows process to get the process ID of its children. So only it writes child ID there, and 0 because a process can have only a single parent, and child can always call get PPID to obtain the process ID of its parent. Okay. Now how this can be done? Okay. Is this clear, everyone? Again, I'll come back here now. Rest of you clear with this? The theoretical concept of race condition. That means when students are asking doubts to a teacher, whom will teacher respond first? We don't know. Same way now, my task is to implement a process in which I'll have two processes. Because sir, you said race condition will occur only when there are more than one processes. Or more than one processes are trying to do something with the shared data, right? So what is my task here now? For the previous two statements, which two statements, Abhishek? Abhishek, which two statements you are talking here?
Sir, just you shown previous slide, sir.
You can type in the chat box, Abhishek, for me. Just a minute. Okay. Now my task here is to write a program which has two processes, and those two processes should do something with the shared data. So now first task for me is to create two processes. Now I know how can I create two processes with the help of fork system call. Okay, fork system call. So I should use fork function in my program. Then once I do that, now those two, child process and parent, should do something with the shared data. So what I'll do here is, now see the sample source code here. Okay, this is all said and done. Directly come to the main. I've defined a function now, character at a time. In the Saturday class, somebody asked me, so what is that char at a time? It's a function name. You can give your name also here. No issues in that. Just I gave the function name as character at a time, which means it fetches one character at a time. That is how the code I have written in that. Okay. So what I'll do here is which passes a single character. Please remember this. Okay. So main is a function program in which I'll create a child process. See, fork, which creates a child process and its PID is assigned to PID. Now, if the PID is less than 0, it writes fork error. That means it has an error. And as I said, fork has two return types. If it is 0, error. Else if it has two values again, it may write 0 or it may write, so it may write to the child. If it is equal to 0, it is writing to the child. or if it is more than that, writes to parent, because I know if it is equal to 0, it writes to child, and more than that, it writes to parent. Now, when it comes here, else if PID is equal to 0, now at this point, I don't know whether the kernel is assigning the time frame to the child process or to the parent process, because as I said, process switching takes place on the load. So kernel decides here to whom it is writing, whether it is writing to the child or it is writing to the parent. Now this is what is look after the kernel part. I may still think that it will give child. So if PID is equal to 0, that means the switching of the process is given to the child. Now it comes here, it goes to the function character at a time. And what is the string I have passed? Output from child. Output from child. So it goes to the definition of the function here. Character at a time. I have passed the string here. Right. So what I'm doing is I'm just defining a pointer here, character pointer, which passes a single character for me each time. So set buff. Set buff is a statement which sets the standard output to null, which is nothing but your output screen. So for PTR, the string point equal to the string which I have passed it, and this not equal to 0, that is the end of the string, right? Put C is a function which is nothing but put a character, put a single character on the standard output. Now what is the single character here I have passed? O. So goes here, output from child comes here, this is here, so O gets printed on the screen. Then again the control goes back, again the control goes back here, again maybe taking the next character, U may be printing here, but meanwhile it is printing here, the kernel may again do a switching of the process here. See, the kernel can't wait for child to complete. If the resources are not available, it may give the control to the parent again. So what is happening? Two different processes, child process and parent process, are trying to do something with the shared data, which is nothing but the same function. And the output, how it comes, it depends on how the system responds. Okay, let's see the output, how it goes here now. I have written the code also for you. You'll understand it. Yeah. See here, the same code I wrote here. I'm not working this on a terminal. So what did I do here is, because every time when you run it, every time the output changes. So what I did, I just gave a for loop here. Okay, that means the same code is running 5 times for me. If you run it on a terminal, /a.out, if you keep on typing it all time again and again and again, your output will change there, which is shown in the slides here for you. See here. First you type /a.out at the terminal, you will get output something like this. Rather than getting output from child, you got O here initially. Now from where this O came, this O could have come from the parent. So when you run it for the second time again the output may change. When you run it for the third time, the output is varying. That means the output of the code every time you run is varying from one time to another time. So this is what happens on the terminal. But since I'm running it on KDeveloper here, I just give it a loop here, which means the same code is running 5 times for me. So you'll understand. So 5 times it should execute for me again. Yeah. It should execute me for 5 times. Rest of coding is same. So till here, it executes me for 5 times. So let's see how this output comes here. This will clear your doubt now. I'll run the code here. Yeah, the output will have got. See here. See the output. How I've got the output. From child, from parent, from parent, from parent, from child, from C, from child, from child, from child, from child. See the output. Now, can you predict how the output is coming? Output here, I thought that output from child. So where is that output? The control has not gone to the child. It started from parent here. So see here, see the variation of the output. In your system also the output may vary like anything. 1043. Okay, see the output, how it is varying. Every time the output is varying here. Here, this was for the first run. The second run again, from child, from parent, see here. From parent, C from parent. See this. HILD came from child, from child. So this is what is nothing but a race condition. Now you can't predict whose output comes first. Whose output comes first. And this is called a race condition. When two processes are trying to do something with a shared data, the outcome depends on how the process responds. Now, this is happening because of the context switching concept. Okay, so how to demonstrate that? First and foremost thing is we'll write a main in which I'll have two processes. Work is used to create a process, as I said. So here there is a parent process and there is a child process. So once this process gets executed, the main thing is here. If PID is less than 0, error. If it is more than 0, there are again two conditions, whether it is writing to the child or whether it is writing to the parent. Now that depends on the kernel. So probably if it gives the control to the child here first, then it comes to this function, goes for execution of this. But meanwhile, if there is a context switching happening, again the kernel will stop here and give the control to the parent. Then comes parent here, parent start executing. Meanwhile, again the kernel may stop and switch back to the child. So switching is happening here, and we can't predict how the switching takes place. And this is called as a race condition. Even I know, see, you think that the very first time the control is given to the child here. Very first time the control is given to the child. But you can't predict that child only will execute first, because it depends on the system scheduling algorithm and resources. So once it goes here, again it may stop in between, depends on the system, okay? It may so happen that it will execute this also maybe from first. After doing this, it may come to parent, or it may come to parent first and child next, vice versa. So all these possibilities are possible for me. Okay, so this is what is called as a race condition. The only thing you should demonstrate is you should write a code where you have a child process, give a function for both the programs, same function, and see how they interact now. See, again now the output is changing here. Here, from parent, again it is executing parent only for 2 times. Now we can't decide it. And this is called a race condition. Clear with this, students? Sir, is the return value 0? Sir, is the return value 0 in PID? It writes 0 to the PID 0. PID is the init process ID, Abhishek. It writes 0 for the init process. Process ID I'm talking. 0 is the return value, not the process ID. 0 writes to the child and it writes the process ID to its parent. Why is that extra O? So that is what Abhishek I'm saying here from the beginning. You can't predict that the output, how the system context switching is happening. See, right now I'm answering your question. Meanwhile, somebody again puts a question here. I'll stop you there itself, and I may go to somebody else's question. Can you predict that? Since you are asking the question to me, it's that I am answering your question. No. Meanwhile, somebody else puts the question there. I can stop you there itself, and I can switch to that question. That is what is happening at the system level also. That extra O is decided by the kernel, whether that O is coming from the child or whether it is coming from the parent. Got it? Is that clear, everyone? You can't at all predict the output. Sir, in code, return values assigned to PID. Where are you talking, Abhishek? Here. Where return values assigned to PID? Abhishek, this is the return value. This is a file descriptor, not the process ID. Whenever a function executes, it has a process ID, descriptor ID. This is called as file descriptor. So file descriptor may have 0 or the process ID, right? It has 2 values. Once it is executed successfully, it writes 0 to the child. So it is coming here now. So if that PID value is 0, it is writing to the child. If it is more than 0, it is writing to the parent. Abhishek, is it clear for you now? It is very simple if you can understand this. Child has, whenever a process executes, it has 2 return values. It writes 0 to the child and the process ID to the parent. So now once this is executed, PID will have 2 values, 0 and the child process ID. Now, where it is writing is decided by the kernel here now. If PID is equal to 0, that means maybe you are in a child process, you are given the control to the child for execution. We are in the child process, so child is executing. If PID is more than 0, you are given the control to the parent process and you are answering the parent process. Clear, Abhishek? Okay, thank you. Yeah, so I'll stop it here. I'll just take your questions. Seventh is absent, okay? Which you did a official online mass bunk on the other day. Please answer this quiz for me and I'll stop it, okay? Yeah, we'll stop the class here. Again, I'm saying the question for the first two is